Hey guys, welcome back to chapter 9. So, what we're going to do now is we're going to take a little bit of a turn in chapter 9. We're going to get into something that you've probably never heard of before, but it's the way that we study energy often in chemistry. So, up until this point, when we study energy as it pertains to chemistry, chemical reactions, we said that we typically study heat. So it's one of the easiest things for us to study. It is a measure of energy. And we said that if we know how much of a material we had, if we can monitor how the temperature changes in that material, and we know what material it is, we can look at how much heat is exchanged, absorbed, or given off in a particular incident. When we study chemical reactions, we often study them in a very specific scenario. So, what we study in chemistry is something called enthalpy. So, enthalpy is the sum of the internal energy and the product of the pressure and volume. So, that's kind of the scientific mumbo jumbo of what enthalpy is. Let me break that down for you a little bit. Enthalpy is really just the same thing as heat. So when we study enthalpy, it's pretty much the exact same thing as studying heat. Enthalpy just happens to happen in a very specific scenario. It happens when the pressure is constant. So let's think about a chemical reaction that might happen in a laboratory. So let's say I have a beaker sitting on the table, and I dump something else into that beaker. I heat it up, and I wait for a chemical reaction to take place. Well, that beaker is open to the room, right? So whatever the pressure is inside of the room is going to be the pressure inside of that beaker. And as long as I keep that beaker open, that pressure is going to be maintained. It's going to remain constant no matter what I do. If I heat it up, cool it down, whatever I do to it, the pressure is going to stay constant. So this is a scenario that we work with very, very often in chemistry. So because this scenario is so familiar to us, we give the heat or the energy a special name. We call it enthalpy. So that's really all that I've done here is I've just done a little bit of a vocab change. Everything else stays the same. So from now on, when we talk about the energy of a chemical reaction, we're going to do it as it pertains to enthalpy. And enthalpy, again, for whatever reason, is denoted by a capital H. Okay? So this formula that I have on the screen, we're not actually going to use this formula. But what this formula tells us is that enthalpy is the sum of internal energy, that's this E here, and a product of pressure and volume. So that's this piece here. When we study enthalpy in chemistry, just like everything else we've done in this chapter, we're going to study the change in enthalpy. So we will always study this delta H. So remember this triangle means delta and it denotes change. So the change in enthalpy is what we're always going to be studying. Okay. So if I distribute that change in, or that delta through this formula, the change in enthalpy is going to be equal to the change in energy plus, well, we're not going to talk about the change in pressure, right? Because pressure remains constant. So it's the sum of the change in energy plus the change in volume. This guy right here, this change in volume piece, that's how we study work in chemistry. So as a chemical reaction takes place, if the volume increases or decreases, that's how we study a work that's been done by that reaction or work that's been done to that reaction. And if you guys remember a couple lectures back, I said we're going to ignore that work piece right now. So if I ignore that work piece, just like we've done all chapters so far, we've got the change in enthalpy is equal to, Oh, the change in energy. So enthalpy, energy, heat, those are all synonyms from here on out in the chapter. I use them interchangeably. If we think about the units for all of those, so what is our unit for energy? Joules. What's our unit for heat? Joules. And what's going to be our unit for enthalpy? Yep, also joules. So here's kind of the summary of this slide, the take home. So the change in enthalpy is going to be the heat evolved or absorbed during a chemical reaction, as long as that reaction's at constant pressure. And we can assume from here on out that we are, in fact, at constant pressure. So that's enthalpy. Okay. So let's get to know enthalpy a little bit better. So enthalpy is probably a word that you've never heard before, haven't heard it often. So we're just going to get to know enthalpy a little bit better with these next few slides. When we talk about the change in enthalpy during a chemical reaction, we're going to give these chemical reactions a certain name. We're going to categorize them. So if the change in enthalpy for a chemical reaction means that we have to add heat into the chemical reaction, if heat enters the reaction, we call that an endothermic reaction. So heat enters into the reaction. So the cold pack is kind of a backwards example. So work with me here. So we have to label ourselves, I am the cold pack, right? So inside of each cold pack, in order for those to get cold, you have to bust something open, shake it, and then it starts to get cold. So when you break that bubble open inside of there, that starts the chemical reaction. So I break the bubble, I shake it, the chemical reaction starts to take place. The chemical reaction inside of that cold pack is an endothermic reaction. It has to take energy into the system in order for that reaction to take place. So when we place the cold pack on our wrist feels cold. Why does our wrist feel cold? Because the ice pack is pulling heat from our wrist into that chemical reaction. So if we label ourselves, I am the cold pack, we are taking heat from the wrist and pulling it into ourselves. So heat is entering into our system. That's endothermic. What do we observe in the surroundings? Well, it feels cold. That's what we observe. In an endothermic reaction, heat is entering into the system. So if we look at the change in enthalpy for the system, so for the cold pack, heat is entering the system, it would be a positive number. So the change in enthalpy would go up. So positive 90 joules, for example. Okay, that's an endothermic reaction. All right, for an exo. So the other one is an exothermic reaction. In an exothermic reaction, enthalpy is exiting our system. If energy is exiting the system, we're going to feel that energy that energy exiting by it getting warm. Okay. So again, the best example of this is fire. So if I am the fire, I'm going to be giving off energy, giving off heat. Energy is exiting the system. If I'm standing in the surroundings next to that fire, I'm going to feel the energy coming off of that in the form of heat. I'm going to feel it getting hot, or I'm going to see it getting bright. So those are two ways that energy is being released. Okay. So in an exothermic reaction, energy is exiting the system. So the change in enthalpy, or the change in energy, would be a negative. So as the energy exits that system, the energy is going to go down. So negative 90 joules, for example. Okay. So we'll use these words endo and exothermic all throughout the rest of this chapter, and we'll come back and drive home this idea of endo entering positive, exo exiting negative. So we'll see that again. The next thing we're going to talk about is enthalpy of a reaction. So when we look at the before and after scenarios, so change in enthalpy, as a chemist, we're going to look at reactants and then products. So we're going to look at how it changes during a chemical reaction. So the enthalpy of a reaction change in this little Rx in here, this little Rx in here is just my shorthand for reaction. So the change in enthalpy for a reaction is the amount of heat that is released or absorbed when a chemical reaction takes place. So to look at this change during a chemical reaction, it's going to depend on a few things. It's going to depend on, of course, the differences between the enthalpies of the reactants and products. So if the reactants are low energy, products are high energy, that would be an endothermic, so our change in enthalpy would be positive, and vice versa. It's also going to depend on the amount of reactants. So we'll see this stoichiometry come back very, very shortly for these problems. So here's an example of a chemical reaction. So what we have going on here is we've got a hydrocarbon that's burning in the presence of oxygen. And when that takes place, we're going to get 2,044 kilojoules of energy released during that chemical reaction. So again, that negative tells me that it's an exothermic, that it's exiting the system. And so that's how much energy is getting released during this chemical reaction. Okay, so the change in enthalpy is going to be a negative number. Okay, that should make sense. So think back to exothermic, right? Exothermic reactions. We've got heat exiting the system. And when you burn something in the presence of oxygen, so you burn a hydrocarbon in the presence of oxygen, anytime something burns, that's likely going to give off lots and lots of energy, specifically in the form of heat, right? You're going to feel that getting hot. So it makes sense that this is an exothermic reaction, that it's a negative number. Okay. Now this piece, dependent on the amount of reactants, there is an inherent relationship between the number of moles of each of these reactants and the amount of enthalpy that's given off. Okay, and here's that relationship. For every 1 mole of this hydrocarbon that gets burnt off, we get a release of 2,044 kilojoules. We get a release of 2,044 kilojoules. So for every 1 mole that breaks down, this is how much energy is released. If we're looking at the oxygen, for example, the relationship would still use this stoichiometric coefficient, this 5 here. So for every 5 moles of oxygen that gets broken down, we still get that much heat released. Okay, if we wanted to look at how much 1 mole of oxygen would release, it would be a number less than this. But if we want to look at the full 5 moles being broken down, then we would get this much energy being released during that chemical reaction. Okay. So now we can tie together this idea of the enthalpy of the reaction, the fact that it depends on the amounts of reactants, and we can do a problem that looks something like this. So let me set this up for you, then we'll work it together. A gas tank on a home barbecue contains 13.2 kilograms of propane, and this hydrocarbon right here happens to be propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. Okay, so let's think about what it's telling us, what we know, what we're trying to figure out. Okay, so what is it asking for? It's asking us to calculate the heat in kilojoules. So the answer that it wants, the end all be all, is going to be an answer in kilojoules. Okay? And what measurement does it take? What measurement is given? The measurement that's given is this 13.2 kilograms of propane. Okay. So we have to find a way to get from kilograms to kilojoules. That's our job. Okay. So as chemists, let me move this over a little bit just so I have the room. Kilojoules. So as chemists, let's start thinking like chemists. As chemists, do we typically deal with a unit of kilograms or grams? No. What's the first thing that we always do when we have grams? We go to moles. So the first step is going to be to go from kilograms to grams of propane. And then from grams of propane, we're going to go to moles of propane. So that should be a step that's getting pretty easy for you guys now. That should be something you can do pretty quickly. How in the world are we going to get from moles of propane to a number that ends in kilojoules? Well, we're going to learn this new skill. We're going to use this new skill we learned. So we're going to use this new equality right here. For every 1 mole of propane that gets broken down, we get this much energy released. So with that equality, we now have a way to get from moles of propane to kilojoules. And we're going to use the relationship 1 mole equals negative 2044 kilojoules. Okay. If we were dealing with oxygen here, this wouldn't be 1 mole. It would be 5 moles. But since we're dealing with propane, we're using this number 1 from the chemical reaction, that coefficient there. Okay. So that's our path. Kilograms to grams, grams to moles, moles to kilojoules. Why don't you guys go ahead and pause the video and get as far into this problem as you can. All right, so let's start working the math here. So we're going to start like any unit conversion that's ever existed this semester. We're going to start with 13.2 kilograms. We're going to start with the measurement given. So the first step was to go from kilograms to grams. So kilograms goes on the bottom. That's the unit we're getting rid of. Grams goes on the top. And then in every 1 kilogram, there's 1,000 grams. So that's going to give us 13,200 grams of propane. Okay. So now I'm just going to change colors and continue working through this problem. So I'm going to move that down here. And then remember, our next step was to go from grams to moles. And I'm going to go through this pretty quick. Hopefully this is easy for you guys now. So grams is going to go on the bottom. Moles is going to go on the top. And how do we get from grams to moles? we're going to use the molar mass. So typing into my calculator, carbon's molar mass is 12.011, and I've got 3 of them, so times 3. And I'm going to add that to hydrogen's molar mass is 1.008, and there's 8 of them. So the molar mass for propane is 44.097. Multiply across the top, divide by the bottom. So 13,200 divided by 44.097. And we get 299.3. We're in the unit of moles, so that's moles of propane. Okay. So those 2 steps are review. This last step is going to be the only step that's a new step. So I'm going to come back up here and keep working on this slide. So I'm going to go back to black. I'm going to take my answer from that step and start a new problem. Oops. 3 moles. All righty. So dimensional analysis, let the units guide our problem. So moles is going to go down here on the bottom because that's what we're trying to get rid of. That's what we're canceling out. So moles on the top, moles on the bottom, that cancels. What unit is going to go on the top? What's our destination? The unit that it's asking for in this case is kilojoules. Okay. So now our units are set up. Now we need to figure out what numbers go where. So moles of this propane, we're going to go to the balanced chemical equation. We're going to take this coefficient and we're going to plug it down here. So for every 1 mole of propane, how much energy is being released? It's going to be negative 2,044 kilojoules. Okay. Multiply across the top, divide by the bottom, so 299.3 times negative 2,044, and we get a ridiculously big number. 611,769, and the unit is kilojoules. Okay. Awesome. So what in the world did I just calculate? I calculated a really big number. So let's talk about what this number means. So this problem, when we set it up, said in this gas tank, it's got 13.2 kilograms of propane. So think about a propane tank. Those are pretty big, right? Lots of propane in there. And if I open it up, and I just let all of that propane burn off. So I turn on my grill and I just leave my grill open and I let it go till the propane's gone. How much energy or how much heat would be given off by that grill? We calculated that 611,769 kilojoules would be given off. That's a really big number. But it makes sense that that's a really big number because if we just turned on our grill and let it go, that would be a lot of heat that would be released, right? So if we did a whole tank of propane, that's a lot of heat released. What are some fun things that we could do with that heat? We could put some hamburgers and hot dogs on that grill. We could put some vegetables on that grill and cook them instead of just letting that heat go out into the atmosphere. So we could use that heat if we wanted to use that heat and do some work and cook some food. But we're not calculating that. We're just calculating how much heat is being released. I hope you guys found this helpful. You're certainly going to see more of these problems, stoichiometry and enthalpy of a reaction. So certainly seek some out and practice. Hope you guys found this helpful.